Hello everyone. Today with us we have Akshat Mishra for this massive talk. He is a third year here at ISI Bangalore. His interests are in probability theory and he's going to give a talk about Markov processes today. Over to you, Akshat.
Thank you, Devansh. Alright, I'll begin. Hi everyone, I'm Akshat, a third year, and today I'll be speaking about Markov processes. So let's begin. Before going on to Markov process, I'd like to define what a stochastic process is. So a stochastic process is nothing but a collection of family of indexed random variables. So essentially you have a bunch of random variables that are indexed by some indexing parameter, and that collection is called a stochastic process. Now, I'd like to define two things related to the stochastic process. The first one is called the sample space, denoted by S, which is essentially the set of all possible values that these xt's can take, and we denote them by samples, and hence the name sample space. P denotes the indexing parameter set. So essentially whatever these indexing parameter values are, the set of all those values is called T, and we can further classify, branch those stochastic processes based on the how the sample spaces vary as well as the indexing parameter. Now I'll move forward to define what a Markov process is. So Markov process is also a stochastic process with an additional property that given the present value, the future values are not influenced by the past values. So an example of a Markov process would be, if let's say you toss a coin a number of times and let Sn denote the number of heads that you attain. So the number of heads is, if you consider Sn, this is a Markov process, because essentially let's say at time n we had k many heads. The number of heads at any time n plus t would be independent of whatever the past values were, because basically beyond the nth step we are tossing those coins independently, and the values of those coin tosses would determine the number of heads moving on from the present value. So this is an example of a Markov process. Mathematically speaking, let's define, let's write the Markovian property. So essentially, as I said, let's say the future value is some xn plus 1 equals y. Given the past values, x0 is some x0 up till xn minus 1 equals small of xn minus 1, and the present value of the random variable xn equals x. This is nothing but conditional probability of the future given the present. So now that I've mathematically defined what a Markov process is, and we've seen one example, I'd like to give some more examples. So one of them examples that I gave was that of number of heads in a coin toss. Another one would be if we consider a die and we roll it many number of times, and we look at the sum of, if we denote Sn as the sum of the first n rows. So that's also Markov process, because essentially, let's say at time n whatever value we had, at any future state, whatever value we are going to have would just depend beyond this nth roll, whatever the die appears. So that's also a Markov process. Another very nice example of a Markov process is a random walk. So I'd like to give an example of that in, let's say, Z. So consider set of integers as your sample space, and you have 0, 1, 2, 3 and so on. It's k minus 1, k and k plus 1. So in a random walk, essentially, again, Sn, which is the position of the walk at time n, that's a Markov process as well. And okay, there are some things that I need to define what a random walk is. So essentially we start at the origin, so S0 is 0, and then beyond that for any movement at any place, what we do is we consider a coin with some probability p for heads and 1 minus p for tails, and we toss the coin. If we get a head, we move 1 unit ahead, and if a tails, we move 1 unit behind. And all of these coin tosses that we are doing are all independent of each other, so they don't influence the outcome of whatever future tosses we're going to do. And so obviously you can see that, let's say you're at the present value is some k, let's say Sn equals k, then we can either move by 1 unit ahead to k plus 1 or k minus 1, irrespective, regardless of whatever the past values are. So this thing is also a Markov process. And the examples that I have given up till now, there's a special thing in this. All of these examples, if you see, S, the sample space, is countable. And we have a name for that as well. So we call such a scenario a Markov chain. So it's a Markov process with a countable state space. Right? And now I proceed further. So let's say we were interested in finding the joint distribution of the random variables x0 up till xn. So if I write that out, let's say it's not equal to x0, x1 equals capital X1, and so on, till xn minus 1, and finally xn equals xn. We were bothered in finding the joint distribution of these bunch of random variables. So what we can do is, if these random variables were given to be a Markov process, a Markov chain, we can use the Markovian property of the independence of future given the present from the past. We can essentially use this fact from probability. The probability of two events A intersection B is probability A given B times probability B, provided that this probability of B and B is well defined, it's positive. So in this case, whatever joint distribution of certain values we are trying to look at, we are assuming beforehand that this probability is assumed to be positive. So all of these values can be taken by these random variables. And based on that assumption, we would like to use a Markovian property, and basically at each step, we'd like to do this. At this step, this is the future value, this will be the past value and present value, and these all will be the past values. So essentially what I'll do is, I'll condition this given the past and present values. So I'll get something, the probability of xn equals n, xn, given all of these past and present values, using the Markovian property, that would just be the conditional probability of the future given the present. Times the probability of these past and present values. And I'll do this process again. I'll consider this as the future value, the previous one as the past present value, and the other values as the past value. Again, condition upon that. And in a similar fashion, we'll be just looking at a sequence of these one-step transition probabilities. And so on, up till the last step, at which I am just left with this, which is just the probability of x naught equals x naught. So what we can see from here is that's of interest is that let's say we were bothered to find the joint distribution of x0 up till xn random variables. This is just a product of a bunch of one-step transition probabilities and times some probability of the initial distribution. So basically we choose, we consider the probability of choosing at the initial random variable x naught equals x naught times those one-step transition probabilities. So given these information, given all of these one-step transition probabilities and the initial law, it's pretty clear that the joint distribution is known to us. So we'd like to formalize that, we'd like to define that. So we define something called the transition probability matrix. So transition probability matrix is some matrix P whose I comma jth entry is nothing but conditional probability of xn plus 1 equals j given that xn equals I. For the remainder of the talk, I'll also like to assume the fact that essentially the probability of xn plus 1 equals j given xn equals I is independent of n. In some sense that basically if we were at I and we went from in one transition to some state j, regardless of whatever the n is, at whatever stage we were at I, it doesn't matter. Whatever matters is the number of transitions that we took from going to I to j. So based on this assumption, we can basically see that probability xn minus 1 equals this given xn minus 2 equals this would be the same as our probability of x1 equals xn minus 1 given x0 equals xn minus 2 based on this assumption. So I'm keeping that in mind, and that's why I'd like to write them down as those one-step transition probabilities, and we look at this matrix which is called the one-step transition probability matrix. Now this matrix is quite useful besides just capturing the one-step conditional transition probabilities, in the sense that let's say we were suppose that we started at x naught equals I and we want to find the conditional probability of some xn equals j given x naught equals I. We can do this by just looking at p, the I comma jth entry of p to the power n. We can see this result from this result that I stated here. So basically what we can do is we fix xn equals j, have x naught equals I, and variate all of these x1 up till xn minus 1. So essentially I can write a summation over x1 up x2 up till xn minus 1, and that thing just comes out to be the matrix multiplication of p to the power n, the I comma jth entry precisely. So in some sense, given that we have written the transition probability matrix, it's easy enough to find all of those transition probabilities for going from I to j for any n number of steps. We just look at p to the power n and look at its I j entry. So in some sense, the matrix multiplication actually captures what's going to happen regardless of whether it was k steps, k plus 1 steps, and so on. So that's a nice thing. Moving forward, based on whatever I have done up till now, you can see this fact that if we look at the transition probability matrix P and look at the I comma jth entry of p to the power r plus s, it's essentially this p to the power r I k is p to the power k s kj, summed over all k in the sample space. This result is quite intuitive in the sense that let's say you started the walk from the ith state and went to the jth state in r plus s units of time. At the rth step, you'll land on some some state in the sample space. So basically I partitioned this as those disjoint events that at the rth step we landed at some state k. So this is quite intuitive. You can also use this result and split it at, let's say if we consider x naught up till x of r plus s, we looked at the joint distribution, and instead of writing it completely, we'll just partition it at the rth step, look at this and the rest, and we basically use the matrix multiplication to get that the initial r probabilities would just correspond to p to the power I k, and the rest would be p to the power s kj. We are using the Markovian property here as well, so you can use the Markovian property as well directly, or maybe use the joint distribution result and proceed and find this thing. Also, here I'd like to note that r and s are all positive for r or s equals 0. P to the power ij is essentially delta ij times 1. So essentially, if I were to write it precisely, p to the power 0 ij is 1 if I equals j and 0 otherwise. This is a definition, so nothing special about it. And yeah. Now I'd like to proceed, and basically up till now we've defined what a Markov process is, what a Markov chain is. I had given some examples. We looked at the joint distribution, used the Markovian property to write this as a product of one-step transition probabilities times some probability of that initial law. Because essentially we'll be choosing where we start, which state we choose to begin our walk with, our path with. So essentially that is also important. And we proceeded and showed that the transition probability matrix sort of distributes in this fashion. This thing is also called the Chapman-Kolmogorov equation, for anybody wanting to know. And now, since I'm done with whatever I have to do with the Markov processes, I'll proceed on to the classification of states of these Markov processes. So, at first, I'd like to define what does it mean for a state J to be accessible through some state I. So, whatever, given the one-step transition probabilities and the initial law, we know everything about the Markov process. We can also think about the Markov process, the state space in some sense, essentially as a weighted directed graph, where the vertices are just those states I, j, k, and so on. And we have an edge from, let's say, some state I to state j, if the one-step transition probability Pij is positive. And we can also say that there exists some path from some state I to k if Pik n is positive for some n. So essentially, if there is some positive probability with which we land from starting at state I to some state k, then we say that there is some path. This is some jargon that I am defining. It's not that important. Now, based on this, what did I mean by saying that some state j is accessible through some state I? Is essentially this fact that some state j is accessible from some state I if and only if p to n ij is positive for some n positive. So essentially we have a path going from I to j. Then we say that the state j is accessible from the state I. Also, similarly, the state I is accessible from state j if we have some m for which pji to the m is positive for some m. And based on this, we are going to define what does it mean for two states to communicate. These double arrows denote that these two states are communicating. And essentially, we say that two states I and j communicate if j is accessible through I and I is accessible through j as well. So the picture would be essentially that you got some state I here, some state j here. There's a path of positive probability from I to j and vice versa. Notice that this two states being communicate, this is a relation, firstly, and this is an equivalence relation too as well, because any state I communicates with itself, because based on our definition, PII 0 is equal to 1, so it's positive. Also, if two states I and J communicate, that would also mean that J and I also communicate, because there's a path from J to I and vice versa. So we have symmetry as well, reflexivity as well, and for transitivity, let's say I communicates with J and J communicates with some other state K. So we got a path from J to K and vice versa. We can clearly see that we got a path from I to J to K and backwards as well. So we've proven transitivity as well. I'm just giving out the ideas, you have to rigorously write this down, but motivation is quite simple. So based on this, we said that I communicates with J if and only if, and this draw the, that is J is accessible from I and vice versa. And since we noted that this relation is an equivalence relation, many of you might have seen in group theory or before, that essentially an equivalence relation is quite nice in the sense that it partitions the whole set upon which the equivalence relation was defined into some equivalence classes. So essentially we will say that any state I obviously belongs to its own communicating class, equivalence class. By equivalence class I mean that I and J lie in some equivalence class C if and only if I communicates with J. So if we define the class, equivalence class in this sense, we can see that it partitions it, because obviously let's say two classes C1 and C2 had some element in common. There will be path from here to here and backwards. So that would contradict the fact that C1 and C2 are disjoint, that they share an element, and they would have to be the same. So C1 and C2 are disjoint, and every element lies in its own equivalence class. So this is a well-defined partition. So that's a nice thing. And now, based on this, I'd like to define the second classification of state. So we look at something called the periodicity of a state. So it's essentially a function of this going from the state space to the set of integers. So we'll be looking at periodicity of a state, let's say of I, and we denote that by d of I. And how it's defined is that essentially I'll first define some set S, not S, I'll say some set, let's say G. G denotes the set of all lengths n such that Pii is positive. So basically what we do is, we look at all those self loops, all of those paths going from I to itself, and we, let's say some particular path was called T, and we consider the length of it, the set of all possible lengths, we denote it by G, and then we define di, d of I, periodicity as follows. It's equal to the GCD of the set, the greatest common divisor, provided that the set is non-null, and otherwise it's defined to be 0. Because it might happen that we start at I and we never land back at I in certain cases, for which we'll define d of I to be 0. Now based on these two definitions of two communicating classes and periodicity, I'd like to write some results. First result is essentially, if two states I and J communicate, then that implies that the periodicity of those states is equal. And the second result is essentially, you got some state I with periodicity d of I, right? And for the sake I am just assuming this to be positive right now, then there exists some n, capital N, positive or natural, such that the transition probability going from I to I of multiples of di is positive for all n greater than or equal to this capital N. I provide an idea of how to prove this result, and I leave this second result as an exercise to the reader, to the viewer. It's simple enough because it requires nothing more than how I define d of I, and after that it can be done without any particular information about Markov process or anything special. So, let's go to prove this result. So, notice that if I show that if di divides dj and dj divides di as well, then we are done. That essentially di equals dj. So we'll proceed that, in that direction, and we'll proceed by contradiction. So we'll assume that di doesn't divide dj. So if di doesn't divide dj, that would mean that there exists some prime p for which p to the power alpha divides d of I but not d of j. Because if this were not true, then every such prime factor of d of I would also divide d of j, thereby implying that this is a divisor of that. So that the statement is fine. And we know that beforehand that I and j, these states communicate. So essentially we got a path from I to j and j to I. And what we look at is the set of all paths for j. Notice that the way we defined the periodicity of the states I and j, dj was essentially the GCD of all of these lengths of all the possible paths of starting at j and going to j. So if we consider all of those such possible paths, the GCD of the lengths of all of those paths divided by dj, where p is essentially a path from j to j. This GCD has to be 1 by how we define d of j. Because if not, let's say this is greater than 1, then that would mean that essentially there is something that divides these all of these lengths and is co-prime to d of j. So that would mean that number multiplied by d of j also divides all of those lengths, hence contradicting how we define d of j. So all of these lengths divided by d of j, GCD of that has to be 1. Now what we'll do is, essentially, we've been given a path from I to j and backward, as well as a self path from going from j to j. But notice that this whole path is essentially a path that starts at I and lands back at I. So we'll use that information, and what we'll say is that the total length of path is essentially some multiple of d of I, call it L times d of I, and I break this into two paths. One path going from I to j and backwards, which is also a multiple of d of I, by definition of d of I, and this other path is essentially a path going from j to j. So this will be some lambda times d of j, right? And we consider the prime p to the alpha that divides di but not dj. Also we'll assume right now, we can make this assumption that essentially p to the alpha is the maximal power of for which p to the alpha divides di and p to the alpha plus 1 doesn't divide di. So based on that, essentially since it divides d of I, it divides the LHS, hence it will divide the RHS as well, which would mean that p to the alpha divides lambda times dj, right? But that would imply that p to the alpha divides lambda times dj for all such lambda. By for all such lambda I mean that essentially this situation is the same regardless of whatever that self path I start from J and go back to J. So this equation is same for all those such possibilities. Hence, for all lambda, I just mean for all lambda dj, as in for all such paths. But notice that since by our assumption e to the alpha doesn't divide dj and this is a prime, so it will have to divide lambda for all such lambda, which would be a contradiction, which would contradict the fact that d of j is the GCD of all of those length of paths, and thereby by contradiction we have proven that di divides dj. And notice that the same argument follows for dj divides di as well, because essentially this these set of states are symmetric in the nature that we have a path from I to j and backwards, and we can then consider all of those possible paths going from I to I and make the same argument, and we'll get the result. So now we have done this result. I proceed to the third classification of states. A very nice classification, which is called recurrence. So recurrence is also a state property. So by that I mean that any state I is recurrent if and only if some particular sum of FIIN is equal to 1, where I'll actually have to define. Without that you won't get what this means. FIIA is essentially the probability of first return to the ith state provided we started at the ith state. So essentially it's the conditional probability that xn equals I, xj is not equal to I for all j1 up till n minus 1. So we don't return back at any of those intermediate steps, and we land exactly at the first time at the nth step. So this is how we have denoted FIIN, and we say that I is recurrent if and only if this infinite sum is 1. And also we have defined one more thing, that FII0 by our definition we will assume it to be 0. So that's the definition. And now based on that, I'd like you all to see that what recurrence essentially means, because it's a very nice property. It just means that the sum of all of these conditional probabilities is 1. It sort of signifies that we've got some total probability coming into the picture, and you might get an intuition that being recurrent means that any state I is recurrent if we start at state I, we eventually land in finitely many steps back to the state I with probability 1. And I'd like to formally prove that. So for that, essentially what we do is, we need to capture, this equation sort of captures these FIINs, and these FIINs basically capture the time of first return, n being in this case. What we'll do is, we'll define a random variable x, and for any event omega, x of omega is n if and only if xn at the nth step we land at I, and we don't land at I before that. So xj is not equal to I for all j going from 1 to n minus 1. So based on this definition and another thing, for all n positive naturally, and if not, if we never return back to the state I for any such n, then we denote x of omega for such an event to be 0. So otherwise, so based on this, what I said earlier would essentially mean that if I somehow show that the conditional probability of x equals 0, given we started at x naught equals I, this essentially captures the fact that we started at I and we never returned back to I in finitely many steps. If we somehow show that this is just 0, we are done. So what we'll do is, for this random variable x, I'd like to write the law of total probability for it, the conditional total probability. So essentially what I mean is that the conditional probability of x equals n given x naught equals I for all n varies. Yes, I'll write the x equal to 0 case separately for some reason. This is one. Because essentially, I've skipped a step. What you will do is, you will write that probability x equals k summed over all k is 1, and then you can, based on that, you can take intersection of all of those with x naught equals I and then divide by x naught equals I, thereby getting the same result. So nothing special with that. You can prove this using the law of total probability and conditional probability. So that will be done. And notice how we define our random variable x. This thing is essentially FIAN, because x equals n if and only if this thing holds. So essentially what we've gotten is that if the state I is recurrent, then this thing is just FIAN, which we already know that the sum of FIAN, n goes 1 to infinity is 1. So essentially these two things will cancel out and we get that this probability is 0. So essentially a state I is recurrent if and only if starting at I, will eventually land back at it in finitely many steps with probability 1. That's what being recurrent means. Note that we can also define recurrence using this particular random variable, which is actually gotten a special name. It's called the stopping time. So I'll define recurrence by an idea called stopping time. Before moving on to define stopping time, I'd like to define what does it mean for an event to be observable up till time n. So essentially we say that some event A is observable until time n if given the information, given the values of x0, x1 up till xn, so essentially all of the information up till time n, we can guarantee whether the event A happens or not. We can guarantee whether this event A happens or not. One example would be, for example, if we consider the random walk and a finite length random walk, let's say of length n, and we denote A to be the event of basically being the time of first return to some state, let's say I. So that will be a stopping time, that will be essentially an observable event, because if we say, let's say A is this thing, and we say that this, is equal to A actually, then time, let's just denote the event, the time of first return to I is, let's say, K. So based on all of the information of x0, x1 up till xk, we know whatever states we landed at for the first k entries, we can guarantee, we can check and we can look at it and we can tell whether this event A happened or not. That whether the first time we returned to the state I was at the kth step or before that or not. So essentially, this is an observable event. I'm just writing up the definition given all of those observations up to time t. And now I'd like to define what a stopping time is. Essentially, a stopping time is a random variable. It's a random variable with the property that essentially the set of all events, if we consider corresponding to x equals k, this is observable up till time k. So essentially, given the first k entries, the first k states, the first k values, essentially x0 up till xk, we can guarantee whether x equals k occurs or not. An example of a stopping time would be the time of first return. So this that we defined earlier. Because if you're given all the information up till time k, we can look at that and verify whether x equals k or not. Also, another example of a random variable which won't be a stopping time would be, let's say, the time of last return. Let's say called y. So, the event, the set of all events corresponding to y equals k, we can never guarantee whether they happen or not based on all the information of x0 up till xk. Because let's say you said that at some time t, y was equal to k, since we are not given any future information, we cannot guarantee whether we land back at k at any further future time. So we need to know all the information. Essentially, we need to know all of the values of all the random variables, and hence it won't be observable until time k. So this is an example of a random variable which won't be a stopping time. And based on this, the way we define the stopping time, we can essentially see that x of omega equals n just implies that it's the time of first return to the state I, hence it's a stopping time. And for recurrence, another definition I can define using the stopping time would just be that some state I is recurrent if and only if the probability that we started at the state I and the time of first return back to the state I being finite is just 1. We can prove this in similar fashion. Actually, we have proven this because when we were trying to show that the conditional probability of x equals 0 given x0 equals I, this is essentially that one. The complement of that is this property of x equals 0 given x0 equals I. This is also conditional probability. Basically, the pi that I have written in the subscript just means that pi is finite given x0 equals I. So that's just a notation. And we can define recurrence this way as well using the stopping time. And now I'd like to do some results related to the number of returns to any state. So I'll define the number of returns to some state, say x. It can be essentially written as a sum of indicator random variables of xn equals x going from all n 1 to infinity. So this just captures the information of the number of visits to the state x. And what we are going to show is, actually I won't show it, I leave it as an exercise. First two results is that if x is recurrent, that essentially the probability of time of first return being finite starting at that state is 1. This would imply that the probability that the number of returns is infinite is 1. So essentially a state x being recurrent just implies that starting at x we will land back at it infinitely many times with probability 1. And if x is transient, we can show the same thing, that probability starting at x and nx equals k. Oh, I forgot to define transient. basically if any state is not recurrent, then we say that it's transient. So essentially, so being transient, this means that there is some positive probability with which if we start at the state x, we won't land back at it, we'll just drift away, drift away from it. So in that case, if x is not recurrent and it's transient, basically if it's not recurrent then it's transient, and then the probability that the number of returns to that state x being k is essentially nothing but 1 minus pi of x times pi of x to the k for k positive, and where pi of x is essentially the probability of the first return to x being finite. So these are two results. I won't go into proving them, I'll leave them as an exercise. Essentially the idea of proving these results is, for the first thing, what we can do is, we already know this stopping time, the way that I defined is essentially the time taken to land back at x for the first time. We'll call that tx, and we'll denote subsequent stopping times called t square x and so on, where essentially t square x denotes the time of the second return to the state x, or in some sense you can say that when you first landed at x and then you're looking at it again, when did you land the second time? Essentially the first time after you landed beyond this. So let's say t of x equals k, and t square x is some k plus t, provided we didn't land back at x between time k plus 1 until k plus 2. So using that and the Markovian property, we can easily show that this probability is 1, and yeah, that's the idea for that. For this result, essentially what we can do is, instead of just directly trying to compute this, we can look at the probability of the number of returns to the state x being lesser than or equal to k. We can find that out, and then basically we'll get this by looking at this probability minus the probability that starting at x the number of returns is less than or equal to k minus 1, and we'll get this result. We can proceed by induction and it will be done. So that's that. These were two results regarding that, and now I'd like to give some results related to recurrence, but for that I need to define generating functions of sequences, and then we will be able to show certain results. So let's begin. So essentially, for any sequence, in our case, we will be looking at those sequences FIIN and those PIJ or PIINs. So I'll just define the generating function for these sort of sequences. The idea is more general, obviously. They use a lot of places. So let's say we're trying to define the generating function of PIIN, the sequence PIN, where I'm just varying n to 0. It's essentially nothing but some function pii of x, which is written as follows. For all x 0 to 1, for this infinite sum to be well defined. That's what I'm assuming right now. Because obviously these probabilities are bounded above by 1, and then this thing would be just be an infinite geometric sum. With if the common ratio being lying in 0 and 1, we can guarantee that the sum is finite, it converges. And based on this, what you can see is that what I do is, let's say we started at the state I and we landed back at I in n steps, we can partition all of those events pertaining to this based upon the time of first return. So in some sense, what I'm trying to say is that Pi of n is summation Fii k Pii n minus k, where k varies 0 to n. Essentially, I've partitioned all of those events pertaining to this based upon the time of first return being k. So this is quite direct and it's intuitive, and you can use the Markovian property and define this as well. So it's not that you can just take my word for it. And what we'll do is we'll essentially multiply by x to the n on both sides to get a result in terms of the generating functions of Pii and Fii. And that would lead us to get a very nice property. And notice that essentially Pii, since Pii is 0, we define it to be 1, and if we don't look at this infinite sum, or then we just look at this, essentially Pii is 0. If we try to compute, the left hand side is 1 and the right hand side is 0, because Fii 0 was defined to be 0. So actually I'll have to take a minus 1 here as well. So I'll just write it out directly and you can verify. Not too hard. Essentially, this thing gets us, the LHS is obviously the generating function of Pii, so Pi of x, which is minus 1, for that minus 1 that I was trying to compensate for, which is equal to Fii of x. The right hand side is essentially the product of those generating functions of Fii and Pi. Because basically if you write them down and you expand them and you look at the coefficient of x to the n of this thing, you just get that it's essentially Fii k corresponding to the x to the k that's contributing in this part, and for the rest x to the n minus k, it's Pii n minus k, so it's quite obvious. And yeah. And based on this, what we'll get is, we can rearrange and we'll get that Pii of x is nothing but 1 over 1 minus Fii. Essentially, the generating function of Pi in terms of the generating function of Fii. What we'll do is, we'll use some result from analysis called Abel's lemma. Essentially, Abel's lemma is just that if you have some sequence En which converges, so summation En and variation to infinity converges, then this would imply that if we could consider the limit of that generating function of that sequence, so an x to the n, right, and goes 0 to infinity, where we're taking x to 1 but from the left hand side. So we're taking the left hand limit. This is essentially nothing but the infinite sum an1. This is called Abel's lemma. And we'll also use a corollary of Abel's lemma, which is essentially this, that if we are also given that, let's say, all of these sequential elements ak are non-negative, and if we know that the limit, the left-hand limit of the generating function ak x to the k from the left-hand side, if this limit exists, and let's say I'll call this a, and this is finite. It can be infinite as well. We can just say that this infinite sum in that case would be the same as this limit. So essentially, it's a result in both directions, where basically we said that some sequence, so sum of the sequence, let's say, converges, then the generating function of that sequence, and we consider the left-hand limit at 1, it's essentially the same as the sum. And for the other side, we need an extra condition for the sequence, all of these elements of the sequence to be non-negative. And if we say that provided this is non-negative, and we look at the limit of the generating function, it's the same as the sum. Actually, I can put this thing as well. Essentially, if this thing diverges, then we can also guarantee that the sum of that sequence is essentially the limit as well. So this is a very nice result, and using that result, basically what I'll do is we'll show this fact that what we do is, let's say I is recurrent. That would imply that infinite sum Fik is 1, which is nothing but Fii of 1. Right. So essentially what I'll do is I'll put 1 here, and using that I'll get that obviously that summation Pii diverges, which is infinite. This sum diverges, and from the other way around, we can also use that corollary to Abel's lemma to prove that essentially we'll assume that this is infinite, and let's say this is transient, and then we'll use that corollary and we'll get the result. We'll get a contradiction that if I cannot be transient. So in some sense, if I were to write the general result of what I am trying to say, is that some state I is recurrent if and only if the summation of all of those probabilities of n-step transitions going from I to I is infinite. This diverges. So yeah, that's a nice result. And using that result, I actually explained the joke that I gave in the abstract of the talk of the drunk man being certain that the drunk man will eventually reach his home, whereas a bird may not. So essentially the idea behind that is we'll be looking at random walks. So the way I defined it earlier, and for the drunk man, we'll just assume that he is walking in R2 or let's say C2, and for the bird, since it can fly as well, so we'll look at random walks in Z3, and what we'll say is that by the line of the joke being that the drunk man is certain to reach home, we'll say that if the state 0 being his home, if it's recurrent, if we can show that this is the state 0 in the random walk is recurrent, then we'll say that yeah, he's certain to reach home, essentially meaning that starting at his home will eventually reach back infinitely many steps with probability 1. That's what being certain means. So we'll show that, and we'll show why 0 isn't recurrent. Not recurrent. In case of Z3, being which meaning that if we consider a random walk, actually a simple symmetric random walk. So by simple symmetric, I just mean that the probabilities of moving in all possible directions are equal, and we start at the origin. So in that case, in Z3, the state 0 is not recurrent, thereby implying that the joke. So what I'll do is, based on this result, what we'll look at is the infinite sum of P00 n. And notice that I'll begin with random walk in Z. So essentially, if we were trying to find out whether the origin is recurrent or not, it's sufficient to look at this infinite sum over all n, right? But the thing is that in Z, if we want to go, we start at the origin and we land back at origin, the number of +1 steps has to be equal to the number of -1 steps for that to happen. So essentially, this thing will be non-zero if and only if n is even. So I'll just look at the infinite sum P00 to n. And since we already know by basic combinatorics that P002n is nothing but 2ncn, basically choosing those plus 1 steps in those 2n number of steps times the probabilities, which let's say as I defined earlier, P2 is the probability of going forward and Q, which is just 1 minus P, the probability of going backward. So P002n is essentially this, and we'll be looking at that infinite sum, but we'll use a nice approximation for the factorials in this, so the 2n factorial by n factorial squared, something called Stirling's approximation. So it's essentially this, that n factorial is well approximated by n by e to the n and square root of 2 pi n, where essentially e is just the Euler's number. And note that this approximation gets better for larger and larger n, so this result will hold in this case, it will be fine. And now, based on this approximation, I won't do the calculations, I just write this thing. This thing just turns out to be 4 eq to the power n by square root of pi n. Right. Now what we will do is, for right now I am not considering the simple symmetric random walk, so P and Q may not be equal, may be equal, we don't know for sure right now. What we can clearly see is that if P and Q being probabilities and the total sum being 1 of essentially moving forward and backward, so P plus Q equals 1, you can using basic algebra show that this would imply that PQ is less than or equal to 1 over 4, with the equality being if and only if PQ equals 1 by 4, if and only both the probabilities are equal and equal to half. That can be shown very easily, and based on that, essentially what I am trying to say is, you get that 4PQ is less than or equal to 1, which would mean that this thing is less than or equal to 1, and we can show that, let's say P was not equal to Q, so by that meaning I am saying that this is less than 1, strictly less than 1, we can show that this infinite sum converges, because basically if we denote 4PQ by some constant A and call A less than 1, this sum is less than or equal to summation A to the n, which is obviously it converges for A less than 1 and obviously positive because the probabilities are positive. So by the infinite sum of geometric saying the common ratio less than 1, this thing converges. So essentially what we say is, if P is not equal to Q, so essentially then the probabilities of moving forward and backward are unequal, then the state 0 is not recurrent and it's transient. And in the special case of P being equal to Q, so essentially P equals Q equals half, so this thing just becomes 1, we can show that this infinite sum diverges. I'll just show it as well. So essentially what you will do is, you can consider this the partial sum up till, let's say, 2n. And what I can say is, this is definitely greater than or equal to the partial sum going from n plus 1 up till 2n, which is bounded above by 2n minus n times 1 over square root of 2n. Because essentially these things would be in a decreasing fashion, so I'll just pick the largest one of them and I'll write this. And this result just turns out to be, this thing turns out to be square root of n by square root of 2. So we get that the partial sum is unbounded, hence the total sum is also unbounded. So in the case of P equals Q, this thing goes to infinity. So if P equals Q, we have that 0 origin is recurrent. And now for the case of random walk in Z2, so in Z2, I'll just write it down. We already know that, you've seen this result, that essentially if the probabilities are unequal, we will drift away from the origin and the state of the origin is just transient. So in Z2 as well, obviously I said earlier that this will be we'll be looking at a simple symmetric random walk, but I am giving an equation that essentially a random walk in Z is also a random walk in Z too. So if we consider the probabilities of moving along the y-axis up and down, or along the x-axis up and down, if they are unequal, we definitely get that it's transient, because if we restrict the movements along just one axis, it's transient by how we proved earlier. So essentially in Z2 as well, we'll assume those probabilities of moving up and down to be positive, and going left and right also to be equal as well. And I'll be looking at a much simpler case where essentially all of those probabilities are just 1 over 4. And what we can see is that P2n 0, 0 in this case is nothing but sum over I and j, where I plus j equals n is 2n factorial divided by I factorial squared times j, which is j factorial, which is essentially n minus I factorial squared. This is essentially what I am doing is I am permuting all of those plus ones and minus ones up and down and left and right. So these are all the number of possible paths times the probability of taking each of those movements, which is 1 over 4 to the 2n. And essentially what I do is I plug this out of this infinite sum. I'll plug the 2n factorial outside with the infinite sum. I'll multiply by n factorial squared on both sides, so in the numerator and denominator, and essentially this thing would turn out to be 1 by 4 to the 2n times 2ncn, because I had 2n factorial by n factorial squared, which is essentially 2ncn, times inside it will just become n factorial times n factorial, which I can inside it is just n factorial times n factorial, which is essentially, if I write it as n factorial divided by I factorial times n minus I factorial, that's just n choose I, and the other is also n choose I. And so essentially this thing would be some times the summation n choose I times n choose n minus I, because nci is nc n minus I, which we already know, and we can prove easily that this is just 2ncn only. Right? So essentially, this infinite sum turns out to be this. This sum turns out to be this, not infinite. And yeah, that can be shown easily. Basically, what you can think of it as, you got too many objects, and you put n of them in one basket and the other n in another basket. And when, if let's say you're trying to choose n of them out of those two n's, what you can do is you can pick out I from here, and the rest n minus 1 is I from here. So using that combinatoric argument, you can show that. Otherwise, you can also use the binomial theorem. You can use look at the binomial expansion of 1 plus h to the 2n, and by combining coefficients, you'll get the same result. So it's not too hard to do. And now that we've given the result for, we've given the value of P002n, using again the Stirling's approximation, we can show that this infinite sum of those P002n's is essentially 1 over pi. Yeah. And since we know that the harmonic sum diverges, we know that this thing diverges as well. And so we get the fact that the origin is recurrent in Z2. For the other case, for the random walk in Z3, we proceed in the same fashion. I won't be doing the calculations for Z3 too, because they're quite nifty. You'll be needing some inequalities besides the Stirling inequality, some inequalities related to the factorials. So in Z3, if we consider, if we look at P002n, this infinite sum, essentially what we'll do is, we'll show that this thing is bounded above by some particular series, which is essentially got some constant by n to the power 3 by 2, and n goes 0 to infinity. It's bounded above by this thing, and as many of you might have seen in analysis, I just write this as some constant k divided by n to the 3 by 2. K, it's a k based on it, but it's a constant. This is constant value is available. And in analysis, we might have seen that essentially sum of 1 over n to the p for p larger than larger than 1. Yeah, this thing is finite if p is larger than 1. We can show that easily. So using that, we get the fact that this thing would also be bounded above by some finite quantity, hence it's finite, and hence the origin cannot be recurrent in the case of Z3, thereby implying the joke. Also, okay, for right now, based on whatever I have defined, I have just considered the case of simple symmetric random walk in Z2, and I have shown that the origin is recurrent. If we consider the probabilities of moving in either of the directions as 1 by 4, there is a stronger result as well. If you just consider the probabilities of moving up and down to be equal, let's say alpha and alpha, and the probabilities of moving left or right as beta and beta, so that obviously the total sum of the total probability is 1, so essentially twice of alpha plus beta equals 1. We can show that the origin would be recurrent in that case as well, and let's say I'm assuming alpha not equal to beta for our sake, and these sort of random walks are called anisotropic random walks. And yeah, we can show that based on some other results and definitions that essentially for such a random walk, if we can prove something called the drift, it's essentially the speed of a random walk. So you would be looking at Sn by n square modulus of that. This will just denote the distance by time taken. So it's just, and the magnitude of that is, we call it the speed of the drift, and we can show that its expected value. This thing converges to 0. I guess expected value 0. So essentially that this drift being 0, and if we can show for any such random walk, if the variance is finite, then we can prove with surety that the origin would be recurrent in such cases. I won't be meddling into that, but I'm just stating that because it's a much stronger argument. And obviously in Z3, since we've shown that the origin is not recurrent, for any d, for any k zk, k greater than or equal to 3, based upon that we have gotten the result that origin won't be recurrent for all such k. So that's a nice thing. And yeah, so based upon whatever we have said about random walks, we concluded about the joke. What I show now is that even though when I was classifying the states of our sample space based upon two states I and j being communicating, we defined something called the periodicity of state I, denoted by d of I. Then we defined recurrence, and basically we defined recurrence as a state property of a state I. What we'll show is that it's a much stronger thing. Actually, recurrence is a class property. So we'll show that any equivalence class, any class C, is either recurrent or transient. So what I mean is that essentially, say I is recurrent, and I and j communicate. I communicates with j. So you pass from I to j and vice versa, implies j is recurrent too. And we can prove that easily by just doing some manipulations. So I and j communicate, that just means that with some positive probability, we can go from I to j. So essentially there exists some n, so that Pijn would be positive. I'll just call it, let's say E. And if I is accessible from j, so essentially there exists some b, so that Pjib is also positive. So I'll be using those two results, and I'll just manipulate this thing. I'll be writing this thing. So this thing, I'll say this thing is greater than or equal to Pji b times Pii n times Pij a. Since I and j communicated, we know the existence of such A and B positive, such that these probabilities, B and A transition probabilities, are positive, and yeah, these are positive. And then what we'll do, I think I erased it, but we had written that a state being recurrent, we've done this result, that I being recurrent if and only if the summation PIIN diverges over n using those generating functions. So essentially what I'll do is I'll sum it over n on both sides, and these being constants, these just come out, and since we know that the state I was recurrent, the infinite sum of PIIN over all n just diverges, and this thing is bounded above by that, so this will also diverge. One thing to note that is how we got this inequality. This can be a strict inequality as well, but it's essentially because if we consider all of those events pertaining to which we started at J, landed at the state J in n plus A plus B steps, the set of all possible events in that, there are some events for which we'll start at J, land back at I at the bth step, then go from I to I at the nth step, and backwards from I to J at the in A many steps. So essentially, this probability is corresponding to those events that are well contained within that, and we already know basic standard probability result that if A is a subset of B, then PA is less than or equal to PB. So that's what I use to write down this inequality and get our result. So it's fine. So based on this nice result, what we have shown that recurrency, defined it as a state property, turns out to be much stronger that it's a class property, in the sense that we had all those states in a state space, all those equivalence classes in a state space S. So using this result, we can say that any equivalence class would either be recurrent or transient. So yeah, that's one thing. And now I'll also show one more thing based on this result, that essentially any such equivalence class which is recurrent is closed as well. So C recurrent implies that the class C is closed, and by closed what I mean is, if we start inside that class C at any such state, let's say I, and we just starting at I, we start moving, and we consider all of those parts of positive probabilities, they will be well contained within this class C, they will not exit it. So that's what I mean. That's what I mean by being C being closed. Now what we'll do is we'll do this result. So essentially, let's say some state I is recurrent. There's some state J outside this recurrent class, and let's say for now we assume that there's some positive probability with which we can go from I to J. So let's say Pij M is positive. I being recurrent implies that starting at I, we'll eventually land back at it in finitely many steps with probability 1. But if, let's say, we had to go from I to J and we were to eventually land back at I again, this would contradict the fact that J lies outside of this equivalence class, since we have gotten a path of positive probability from I to J and vice versa. So you'd get a contradiction, right? And yeah, that's the idea that we'll do, that we'll use to prove this fact. And also I'm leaving some rigor behind. I'm not writing this properly, I will set it out properly. What we'll be doing is, we'll assume, let's say that PMij is positive, and we'll say that, say we don't land back at I in any finitely many number of steps. What we'll say that the probability of that happening, that essentially at the nth step we were at J and x equals 0. By x equals 0, I mean that we never landed back at I, starting at I, right? Provided we started at I initially. This thing, if we somehow show that this is 0, that would basically contradict a fact, or assumption. For now, we had assumed that this probability is positive, but the problem is that this probability is bounded above by the probability that x equals 0 given x not equals I. Because x equals 0 and xn equals a, at the mth step we landed at the stage a, the events pertaining to this condition are well contained within this. So using that a subset b, p8 less than or equal to pb, we would have shown that this means that this probability, conditional probability, is positive. But it contradicts our assumption that I is recurrent. Because for I recurrent, I showed that this probability is 0. Hence we get a contradiction, and this is rigorous enough. And yeah. So I had shown that, okay, recurrence starting as a state property turned out to be a class property, and any recurrent class is closed as well. We'd move further to other results as well. So this is a result that I'm just stating for now. I cannot prove it right now because we'll be needing a strong Markov property for it. But the result is quite nice, which is why I'm writing it down. So essentially any finite closed class, by class I just mean those equivalent classes, it's recurrent. We'll be needing a much stronger property than this traditional Markovian property, or the strong Markov property, where essentially these indices, right now we're assuming them to be constants, we'll switch them by the stopping times that we defined earlier. So in that strong Markovian property, we'll have stopping times here, and we'll say that, let's say we landed at xt equals I and we had some past, the future would just be, the conditional probability of future would just be the probability of future given this, and all of that would vanish. So we will be needing that to prove this rigorously. I won't be meddling into that right now. There are other results that using generating functions we can prove as well. So earlier we had proven that I is recurrent would just mean that infinite sum PIN diverges. By that I mean that sum of all of those probabilities and step transition probabilities is infinite. And we had also shown that being recurrent would imply that starting at that state, we'll eventually land back at it infinitely many steps with probability 1. There's a much stronger thing that we can say, that essentially the probability that you start at I and you visit I infinitely many times, infinitely often. If I is recurrent, then this thing is 1. I won't be proving it. We need those generating functions. It's not that hard. We'll be just using some induction. Basically what we'll do is, we'll consider this to be QII, and then we look at QNII, QKII, let's say. QKII by QKII just mean that it's the probability that we started at I and we visited the state I k many times. That's right. So using that in generating functions, we get this result. I'll just provide an intuition for now. Basically, let's say a state I is recurrent and this probability is not 1. What would it mean is that with some positive probability, we start at I, so at time 0 we were at I, and we will be only able to visit finitely many times, let's say call those times t1 up till t2 and so on up till tn, at which we will visit the state I, right, with some positive probability. But this thing actually contradicts the fact that I is recurrent, since if we just start looking at our process beyond Tm using the Markovian property, we will be able to see that starting at this time, we never landed back at I again. But I recurrent would just means that we'll actually be guaranteed with some positive probability we'll return back to it infinitely many steps, which is being contradicted here. So that's a nice intuition why this probability has to be equal to 1 exactly. So that's another nice result. Based on this, we can also show other things as well. That's essentially, if I is a recurrent state and J is another state that communicates with I, then we can say that probability that we start at A and we visit J infinitely often, that's also 1. So we can show those results as well. I won't be meddling into those right now. I'll be just moving forward to the two types of recurrence that we'll see, and why we define them in that sense. So essentially, recurrence was a very nice property that captured a lot of intuition that we had about what does it mean for us to be certain to land reoccur back at some state again and again. That's just recurrence. Why do we need those two types of recurrence that I'll be defining? I'll first write them out. There's a thing called positive recurrence. There's another thing called the null recurrence. So essentially how we classify these two types is that, let's say a state I is recurrent. I'll just write R for now. If a state I is recurrent and we look at the expected time taken for the first return to that state I. So starting at I, look at the time of first return. This thing, if this thing is unbounded, if it's infinite, we say that it means that the state I is null recurrent, otherwise it's positive recurrent. So essentially expected value 5 is infinite, and in this case expected value 5 is finite. Note that both of these cases can occur, because essentially if we look at the probability distribution of Ti and we say, let's say the probability that Ti equals k is 1 over k squared, then that would imply that the expected value of Ti starting at I is just 1 over k, summation of 1 over k, which is the sum of harmonics with diverges. So we have a case of null recurrence, as well as if we consider, instead of the probability of Ti equals k as 1 over k cube, this thing just turns out to be summation of 1 over k squared, which a lot of you might know as the basic sum. So it's just pi squared over 6, and it's finite. So we also have a case of positive recurrence. We can show this without just stating it as pi squared by 6. We can just write it out this as it's lesser than or equal to summation k and times k minus 1, and then look at this telescopic sum. We can write this as 1 over k minus 1 minus 1 over k, and all of those cancel, and we get that this thing converges, and this converges as well. It's finite. So based on that, we've defined those positive and null recurrence. But why the need for that? The need is because of the following result. See, recurrence is a nice property in the sense that if we have a class, because we state it as a class property from now on. So what do we mean if we say that a class is recurrent? It just means that if we have this thing, let's say the class C is recurrent, you'd have something called a stationary measure. Basically, if let's say C is recurrent, that would imply that there exists a strictly positive invariant measure. That's what we are guaranteed by a class being recurrent. But okay, measure just means that we have all of those axioms of probability, those three axioms, besides the axiom of assigning the entire weight of the sample space to 1. So in measure, let's say we define the measure map by mu of A need not be 1. So it can be anything in 0 dimension. It can be unbounded as well. So that's just a measure. But if we look at the cases of positive and null recurrence, they guarantee us something more. In the case of a class being positive recurrence, we can show that these are also class properties. I won't be doing that right now. But for a class to be positive recurrent, it would mean that not only we have a strictly positive invariant measure, we have a unique strictly positive invariant probability measure. So essentially we have a probability distribution, an invariant probability distribution as well upon this. And by invariant, I just mean this thing, that a probability distribution pi to be invariant is just that pi I is summation pi j times pji, j lies in the sample space, state spaces. So essentially, a probability distribution to be invariant, it just means, if we look at it that way, if you look at it as a matrix multiplication, it just implies that pi equals pi p. But that would mean that this is equal to pi p squared and so on. So essentially, if a probability distribution, if we have an existence of such a stationary or invariant probability distribution we denoted, that would just imply that essentially if we were supposed to look at the initial law that x naught equals I, this probability is the same as we start our walk, start at any state j, and we eventually land back at I at the nth step. That probability is the same as the initial distribution as well. So this is a very nice thing. You can use it in branching processes. Basically, essentially, it's a memoryless thing. If we know such an existence of a stationary probability distribution, that essentially, let's say we had some branching process and we wanted to bother about, let's say at some node, what's the probability that we land back at this node at the nth step. If we know that the model that we've used the model is Markov process with this being a positive recurrent class, we can just say that the probability that we land at this node at the nth step is just the same as the initial law that we started at. So existence of stationary distributions is very nice in that sense. Yeah, so those were our results regarding the types of recurrence, and I won't be able to prove all of these results because of time restrictions, and yeah, I think that's that.
So yeah, does anybody have any questions?
Existence of stationary distribution, it always exists or not always, right?
No, not always. I said that essentially the stationary distribution, if you look at a recurrent class, we have its existence, but not for a probability measure, but for a measure. Essentially meaning that the entire weight for the sample space, it may be unbounded, it may be anything else. It may be bounded or
Even in recurrent states, it should be non-null.
Huh?
Even for recurrent states,
Huh?
the state should be non-null recurrent.
That's for the probability measure. I'm talking about just a measure. So for a measure, you just need recurrence. For it to be a probability measure, as well as any positive recurrence implies that. That's it.
What are your references?
Okay, my references for this would be two books that I used. One is a book by Carlin and Taylor. It's called The First Course on Stochastic Processes. And the second reference is a book on Markov processes by Etienne Pardue. These are two nice, very excellent books for looking at Markov processes and a lot of things in general. And yeah, this book I recommend for a first reading, and after that we can just do our Etienne Pardue.
So yeah, seems like there are no more questions. So yeah, let's thank the speaker once again.